Okay, for this module, it's data management 2. So we've gone through intro to R markdown, dplyr with the pipe, and some of the rounding and other functions in the data management 1. So this one's going to go through lubridate along with some of the other functions within dplyr like separate and unite and joining your data together. So let's load the Tidyverse as well as our fish data set that we've been working with. And again, this is a fish data set from the Upper Mississippi River Restoration Program's long-term resource monitoring element. It's community data from 2018 for 6 different species from this long-term monitoring uh, station or across 6 different field stations. So first we're going to talk about lubridate. Lubridate is a package that's created after the initial Tidyverse packages, so it has to be loaded separately from the Tidyverse, and it was created to handle easy date conversions. So we're going to dive into a couple useful functions, and this is just scratching the surface of lubridate. So the syntax of lubridate is to denote month, day, and years as M, D, Y. Very simple. And you can convert among these date types like month, day, year, month, date, etc. And you can do the same things for hours, minutes, and seconds, which are just HMS. So again, very simple. Lubridate is the Tidyverse's answer to the POSIX package and the POSIX date system, which whenever I see that code, I have no clue what's going on. There, lubridate has made it a lot easier for me to understand how to convert dates within R itself. So you bring in the lubridate package here, and what we're going to do is just say, let's take the S date column, which is this one. Right now it's a character, and it's month, day, year. And let's make it a date so we can do other analyses with it or other functions. So the simple function for that in lubridate is just MDY for month, date, year on the S date column. Again, remember that the fish data with the $sign and the column name gets at that specific column. So we're going to name this just as date. We're saving it as object date. So if we look at date, we see it's a date column format, and now it changed it to year, month, day automatically. We have month, day, year here because that's what it's in, but lubridate typically works in year, month, day, so it's just going to change it. It doesn't change any of the data itself, it just changes the way it looks. Here we're creating a date time variable. So this is month, day, year underscore HMS for hours, minutes, seconds. This is a function within lubridate, month, day, year underscore HMS. We're creating a date time variable. Sometimes you'll see this in a lot of data sets, especially older ones that have date and time smushed together. So what we're doing to do that is use this paste function. Paste just takes whatever you put in there and it'll just like put it together. So what this looks like then is the fish dataset's sDate column followed by the fish dataset's sTime column, which time here is hours, minutes, seconds. And it's actually in an HMS format already, which is pretty cool that R read it in that way. So what this looks like with just the paste is it's literally taking the date, separating them by a space, and then the time. That's what it's doing for that. Here we're converting it to a time or date time variable. So what that looks like then is we've got our date and our time, and we have a time zone. Sorry, I blanked on the word for time zone. UTC, it's unspecified time zone right now. or universal time because it's unspecified. Okay, so now we have this data set, and let's say, what does this actually get us? This just gets us what here for this, our date and our time together. But so these things are really easy to do is just month, date, time, month, date, or sorry, month, date, year, hours, minutes, seconds to convert these things. What does that actually do for us? Well, it helps with some of the other functions that we have been using. So if we were like arranging by date or something in a data set, remember our fish data set, the date variable originally was a character. So let's say we want to arrange by date. So we want the earliest date at the top and later date at the bottom. What arrange does on characters is it takes the first value and arranges that way. So all of these are October 1, 2018. Keep going down. October 1, October 11, 15, 16, October 2, then what it's doing is taking everything as it comes. So 1, 0 is earlier than 7 for July, for example. 2 is later than 1, 0 or 1, 8 or anything like that. So it's just arranging it alphanumerically, which is gobbledygook for a date. So if we make this a date and we say take the fish data, mutate S date, so we're writing over S date, and make it a month, date, year column of S date. So what that does is make it a date variable rather than a character. And again, it changed it to year, month, day, and that's just because that's how lubridate works, but it saved it as the month, date, year for your character variable. And then now we say arrange this data set. So same thing as here where we arranged it, that was a character. This is now a date variable, and we are arranging that. And now it actually arranges by earliest date. So we have June 15 as our earliest date. And as we move down, lots of June 15s here. June 18, skip down a lot more. Still June 18, June 19, June 20, etc. It actually arranged it by date rather than character string. So this is a really handy way to use that with a range. And this is just like one specific way to do this. But creating dates can really help with plotting data or arranging your data, grouping it, filtering it by these different dates rather than having them be characters. So, and also sometimes with your date columns, a lot of times when you are manipulating your data or wrangling it, you might just want like a year column or a day column or a month column. And instead of doing something like what we'll look at the end of this lesson with separate and unite, you can actually just extract the years as a new column using the lubridate. And this is, we have our date column. That was what we made here was month, day, year of just our date column, and then date time was day and time. So we're using those. We can extract the month, the day, and the year, assuming they are already in a date format. So month, these are just all the months extracted, the day, all the days extracted, and the year, all the years extracted. So that's cool, but what does that actually mean for our data set is we can do something like put it in mutate. So if we copy this code and we say we want a year column, so we want year, and we're just going to say that equals year of S date. And S date is, I guess we have to also make it a date here. So we'll do that. So first make S date a date variable, and then use mutate to make a year column by extracting the year of S date. And we're gonna just select year because otherwise we're gonna have to scroll to the end. But what this did was take out the year variable from our entire data set, which for the entire data set is 2018, so not super helpful. But we could do the same thing with month, for example. So month, and just extract the month of a date variable. Hmm, column year. Oh, duh, that month there. So now we have July, June in there, August, September, October. So that extracted the months from our date variable specifically. So these have to be dates. Same with this has to include a time variable. So if we took our date time, which again was date and time paced together, we ask, give us the seconds of that, which are just zero for everything. The minutes vary quite a bit, nines, 20s, 29, 40, etc. And then hours all over the place as well. So this is going to extract components of this, and this isn't very useful just as is until you put it in something like you're adding a new column in your data set, or you're using these as some sort of function in your data to create new columns to look at differences in time, something like that, etc. You can also round dates and times to any number of variables that you want. So things like this, you can do half seconds, seconds, minutes, 5 minutes, 1 hour, a day, 1 week, a month, 2 month, 3 months, 6 months, year. So you can round your dates, creating something like bins, seasons, things like that. To do that, it's round date. So last module we talked about rounding. This is rounding for lubridate specifically, round underscore date. Again, we're taking our date variable, which was just year, month, day of our data. We're saying, what is our unit going to be? Our unit out of these. We're taking week. We want to round to 1 week. And we want our week start for here is 3. So I think the default in R is like a weird week start date. It's like Wednesday or something. Or maybe I'm just misremembering, but like you can change the week start to be Sunday, Monday, Tuesday, Wednesday, whatever day you want. And that's what this function is just week start equals get option, lubridate week dot start. All of this is like just code I copied, and then this changes the day of the week start. But what those will do is then change all of your dates to be a week start, rounding up or down here. It's rounding to the nearest week. So these are all August 15, all September 5, instead of just being other dates. So this might be creating week bins. So this one is without this week start thing, just if you wanted to play around with what day of the week starts on, Monday, Sunday, whatever, this is how you would do it and just change whatever number this is to be whatever day you want it to start on. So round date, just plain, this rounds to the nearest week up or down. So we have a different week start than 3, whatever 3 means here. So now it's 7/22 is our week start instead of 7/25. Floor date rounds down to the nearest week. So this is just rounding up or down like a regular rounding. This is rounding down to the nearest week. So some of those numbers change. This one, ceiling date, just like the rounding last module, floor and ceiling. Just ceiling date rounds up to the nearest week. So 7/29 instead of 7/22. It's just rounding up. Round date we have date time here, and then unit, we're rounding to the nearest hour. So these are all the round date function or floor date, ceiling date, and then we're just including whatever we want, our hour, our day, our week, our month, our bi-month, our quarter, etc. So this one is just hour, and we are just rounding to the nearest hour. Instead of them having a bunch of minutes associated with it, it's just up or down on those minutes. So those are different ways to bin by hour, bin by week. You could do quarter. Let's say quarter here. Round date now makes July 1, a bunch of them, October 1. So this would be by quarters that are inherently specified in R. And then you can use things like week start, or there's got to be other functions to be able to change when those quarters exist too, or when those half years, etc., things like that change. So this is a way to round, which is very handy, very quick. And then make sure if you are using these rounding things to use them in a mutate like we did here, if you want to save those data and add them to your data set. So these are just the functions by themselves, but add them to mutate, add them to summarize, things like that. One of the handiest things I think with dates and times is that if you have data from multiple collaborators or different years, you likely want to check the time zone or other aspects of those data to make sure that they are correct. Like make sure the date format is the same among your data. Make sure that time zone is correct among your data. And it's really easy to be able to manipulate that to be in the same time zone or to be in the same date format and then append your data together with these lubridate functions. So this is an explicit example of using time zones because a lot of times like I might be in Central Time or another collaborator's in Eastern Time in the US, so we need to change for the times to be the same if we want our data to mesh up. So this is all of the valid time zone names, Olson names. Many, many time zone names, overwhelmingly time zones. This will give you a time zone for your data. Remember, our date time is the date and the time that we pasted together from our data set. TZ on that gives us UTZ. Coordinated Universal Time for all time zones worldwide. It is the default for R if a time zone is not provided. I know UTC is not the time zone for these data, but that is what we didn't specify what it was when we converted to hours, minutes, seconds. So let's say we want, this is what it is for now, whatever, specify it in your previous data to make it more accurate in your functions. But let's say we want to change the time zone, but not our time specifically. It's really easy to do time zone conversions. So let's say force time zone, because we know these LTRM data were taken in Central Time in the US, or America Chicago time. We don't want the time to change. It's as this coordinated universal time. We know it's wrong. We know it's Central Time Zone or America Chicago. We can force it into a new time zone using force underscore TZ for force time zone. Or date time column, date time data, say time zone T zone equals one of the many Olson names for your time zone names. America Chicago is the Eastern time zone in the United States. What this does now is it makes it S or CDT for the Central Time Zone. This is what we want our data to be. Let's just make sure it didn't change it. This is 9:20, 8:09. Let's check our old date time. Still 9:20, 8:09. This is a way to force it into a different time zone. It was UTC. After this function, it becomes Central Time. Did not change the actual time though. If you need to convert your data into a different time zone and change the time because the time zone it's in is currently correct, but you need your data from the Eastern time zone and the Central time zone to be in the same exact time zone and those hours, minutes, seconds change, you use with TZ. So you're not just forcing a new time zone on it, you are converting the hours to a different time zone. So specify our data is date time, our T zone or time zone equals America, Detroit. Let's say we want to change it to the Eastern time zone, which Detroit is in. All of these data shift by 1 hour. It does change quite a bit here. Or it went from universal time to not, sorry, went to universal time, not to America, Chicago time. So maybe let's change this time to make it a little bit easier to read or see what it does. Central time here, we're taking that central time and we're converting it to Eastern time, America, Detroit. See what this does. I don't know why it keeps jumping down. It's now 10:20 instead of 9:20. It's now 9:09 instead of 8:09. It changes it by an hour and gives the new time zone of Eastern time. This is exactly what we wanted, exactly what we had to do here. Earlier, it changed the time zone completely or changed the time a lot, like to 5:20 here, because it was still in the universal time rather than the central time zone. And then sometimes it's helpful to calculate time intervals between dates or times to know the duration of something. So this is a function called diff time, so difference in time. And we could just say, what's our diff time here? What's our difference in time between, in our data set, we have this F time variable, which is finish time of the survey, and our S time variable, which is start time. And we want to know what the difference in those is. Maybe we're calculating things like catch per unit effort. So like how many fish are caught in a specified time. Maybe these different sampling events take different periods of time. So we need to get really at like the number of fish per time to get a better estimate in comparison. So we know in our time we want to calculate a difference in the time here between the finish time and the start time. And our time zone is America, Chicago. Was the central time zone. And our unit we want the differences to be in is minutes. Here we can put hours, seconds, seasons, or quarters, or months, weeks, whatever we wanted there. But we just want minutes. So this calculates the differences in time. This is negative 93 minutes, so 93-minute difference, 26-minute difference, 26, 26. There are positive values and negative values in here. I'd have to actually look to see what those are, but I think it's because they're different dates. So a lot of these data are like net sets that are left in for 24 hours, 25, 26 hours. So these negative differences are going to be like an extra day. And that's something, if you have things like this where they're negative numbers or something, you want to see what the date is as well, not just the time that's specified. So in this data set, the electrofishing transects are 15 minutes, and then we see a lot of 15, so that makes sense. But all these negatives are likely the net sets that take place over 24 hours or more, and that's why they have different numbers here. So if you have something like that, make sure to also include the dates in this and not just the time itself. So that's it with lubridate. It's a very, very, very slim amount of information there because it's just trying to scratch the surface. There's so much going on with lubridate that you can do to make using dates and times a lot easier for your data. But next, we're going to talk about related data. So these are data sets that you want to merge together into one data set to make it really easy to compare. So maybe you're comparing things, multiple data sets like zooplankton and fish within a year or across months, and you have two different data sets that you want to combine together. So then you can easily do analyses or figures on that combined data set. So you can do everything in R using this function merge, which is base R. However, there's often a lot of issues with using merge, or it's not as straightforward as people think it is. So I recommend, like most things, using tidyverse functions, and these are the joining functions, which include inner join. So any data between your two data sets that don't match with one another are excluded. Right join are all observations in your second data set you specify, which is the right data set when you code, are included even if not matched. Left join, all observations in your first or left data set you explicitly say are included even if not matched. Full join includes all combinations of data, so it doesn't exclude anything. Semi-join only keeps your matched observations completely. Anti-join only keeps observations without a match. And so these are pretty like abstract, but I'm going to get into them more explicitly to talk about and make sure we understand what these look like. So below are very simple examples to visualize these types of joins. This is just combining related data. One, they need a data column, at least one data column that are similar between the two data sets. You need like species ID, year, something that matches among your data sets to be able to combine them together with a join. So we're going to start off with inner join. But first we're going to create these simple tables. We're just creating two tables just to make it easy. 3 rows of each banana, 1, 2, 4, and Y, Y1, Y2, Y4. And this first tibble was banana. So banana is in common here. 1, 2, 3, and X, X1, X2, X3. So we've got one data set with banana and X, one data set with banana and Y. That common variable is banana. So an inner join, what you do for all of these joins is the same exact thing. We say inner join or whatever join you are specifying. Here we're saving an object. We're saying the first data set, the second data set, and then what the joining variable is. So by equals banana, join by. So what this looks like for an inner join is it only keeps the data that's matched. And they matched for row 1 and row 2 because there's an X1, a Y1, a banana 1, banana 2, I mean. X2, Y2 here. So they are now matched by the ones that were similar. So inner join, unmatched data are excluded, which is basically the same thing as semi-join. So you can use either one. Exclude those unmatched data. We do not have X3, we don't have Y4 in here. So that's an inner join. Outer joins keeps observations in one or both data sets, unlike the inner joins. So the left join here is just function left underscore join. Specify your first data set, specify your second. If you only have one variable in common and they are named the same thing, you don't actually have to specify this by function. Because our data sets are very simple here, it's just banana and X or banana and Y, we don't have to specify it. If you want to, you can. Doesn't harm anything. But because our data sets are so simple, you don't have to explicitly state what we're joining by. So the left versus right join is literally just, this is the left data set, this is the right data set. So if we run this, it's keeping everything in this left data set. So this included the X's. So it's saying keep everything from the X data set and exclude unmatched things in the Y data set. So we've got Y1, Y2, and NA, and we don't have that Y4 because it excluded it because there was no match in the TIB1 data set. Right join is going to do the same thing, but for the right data set or the second data set you specify. So now we have Y1, Y2, Y4, and an NA for banana 4 at the X. So it's just the opposite. We've got Y, X left here, and we're keeping our right here. That's just the nuance. Use either one that makes more intuitive sense to you. You can flip these and they would be coming out to be the same. If you flip TIB2 with TIB1 here, it's the same as this first data set, except now we just have Y at the beginning and then X. So whatever you feel most comfortable with using. Full join is going to keep everything from both data sets. So now we have banana 1 through 4, and we have an NA with X and NA with Y3. So that keeps everything in both data sets. And an anti-join is going to keep observations that are in the left data set, but not the right. So it's keeping things that are unmatched. So anti-join, where we have the X's first in TIB1 and then the Y's. What's not joined is banana 3, X3, because there's no banana 3 in the second data set. And if we just switch that to be anti-join with the TIB2 first, it's just going to show us banana 4, Y4. This is everything that's unmatched in those data sets. So it's just taking out what was left over, basically. So these are just really simple ways of visualizing your data and or combining your data, not visualizing it, sorry. So very simple ways to visualize what those inner joins are doing using very simple data sets. And I've done these with data sets that are thousands to hundreds of thousands lines long, where we're joining those data by year, by barcode or species ID, by anything that you want to join by. I do want to specify if for some reason you have, or this is not for some reason, this is quite common. If you have data sets that have different names of the same column, let's say like year and year. So we're going to just give an example. We're not going to run this. But if we want to do like left join of maybe we have fish and zooplankton, and we want to join them by the year column, but the year column spelled differently in your data set, you can say by equals concatenate for the C function, parenthesis, if it's spelled capital Y year in the fish data set, but it is just YR in the zooplankton data set, this is how you code that. You can change the names beforehand using rename if you want, but if you just want to say we're just joining them, it's okay that they're different names. You don't need to do that rename step. You just say by equals, make sure this concatenate is there. Year equals YR. This is from the zooplankton data set, the second one. This is from the fish data set, the first one. So just make sure they match which ones are there. That's an easy way to do that. What also is helpful is if you have your data sets, and let's say you want to join them not just by year, but by another variable like sampling site. So what you do is just say, okay, join by multiple variables, concatenate. So by equals concatenate C here, variable one, comma, variable two, and you can just keep adding more variables if you want. It's just a way to increase that ability to get more fine detail with how you are joining there. So this is like I use joins all the time because I'm using multiple data sets, and it's so helpful to just think about I don't have to rename my data. I can use this year equals year thing. I can join by multiple column types, etc. So one thing that's also really helpful is maybe your data are just they're all ready to be joined and they just need to be tacked on. They have the same exact columns and rows, or at least similar columns and rows, no name changes, nothing. You can use bind calls and bind rows. So maybe you just have to tack on extra columns or extra rows of data. In base R, it's cbind and rbind if those are familiar. But within base R, both datasets must have either the same number of columns or the same number of rows, and it's literally just going to tack on those data. Does not matter if the years don't match up in rows, if the columns are out of order, it's just going to tack them on, and then your data might be really messed up. But if you use bind calls or bind rows, you don't necessarily need to have the same number of rows and columns. You have to have the same column names for them to be placed in the same column, but you don't have to have all years included. You don't have to have all of the same columns included. They just have to have the same names if they are similar between the data sets. And what R does with bind calls and bind rows is it then can move your data columns to be placed in the correct location with your other data sets. So this is actually very helpful, and I'm glad that they updated this more recently to use these functions. So we'll see what we do with cbind here. So again, we have, this is base R, tib1, banana and X, tib2, banana and Y. If we use cbind, this is a column bind. So it's tacking on extra columns of data. So we have banana, X, banana, Y. So it's going to repeat our data. There's nothing about matching up banana with banana here. It's just tacking on rows or columns of data. However, if we use bind calls, same thing, just instead of cbind, just bind calls. What it does is it creates two versions of banana here. Banana dot 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 1, X, banana dot 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 3, Y, and it has that information there. It does the same thing as column bind for cbind, but it changes the variable name so they're not the same. If we use rbind for base R, you can't do it because our column names don't match the previous names because tib1 has an X column and tib2 has a Y column. So at least it gives you that error and doesn't tack on those data erroneously, but it sometimes might if you don't specify certain things. If you use bind rows, on the other hand, this is what I find really helpful, is that it creates new variables and fills them in with NAs. Or not new variables, but it tacks on those rows and fills in the rest of those data columns explicitly with NAs. So we have banana here, and then X and Y. Unfortunately, it doesn't like match the bananas together here using just the base function. Because we still have 1 and 1 and 2 and 2. So if you wanted them to like match to say 1 and put Y1 here, 2 with 2 and put Y2 here, etc., use a join. But if you're just tacking on data, so like banana might not be like row number, it might just be a count of bananas or something, this is the perfect way to do it. Just tack on those data. It's going to line up your variables, make sure you have all the columns there, and fill in those explicit missing values if they're there. And then finally for today, we're going to go over separate and unite. So these are very helpful because they take apart components of a column or combine multiple columns together. I use these a lot for date times, for scientific names, for to get like genus and species columns, etc. Also, you a lot of times, like in old data sets, you're gonna have a lot of smushed columns together, and then it's like, why did they put all like five of these columns in one column? It just doesn't make sense. So separate is an easy way to pull them apart. So separate, like it says, takes apart, separates multiple values that are in the same cell, same row and column. It will split the values based on some sort of separator. This is in the tidyr package, which is part of the tidyverse. Let's look at our fish data set, and we're just going to use the F date as an example. We saw how to do this to separate month, day, and year using lubridate, but this is a good example as well here. F date. We want to separate this into month, day, and year. So we want to pull apart these components. So we say separate, specify which column you're pulling apart is F date, and then you just say what components you're pulling it apart into. So into equals concatenate, month, day, year, because that's the different components that are separated by the forward slash. And then we're just going to select some of the columns to look at just to make it easier. So we have month, day, and year, and it gets rid of the F date column, so we no longer have that one. So separate automatically separates values based on a non-alphanumeric value, so the forward slashes. But you can also specify the separator as well. So in addition, it also maintains the column type of the original data. So all of these were originally a character like sdate was. So all of these are also a character. If we want to change the resulting columns, like month, day, and year, we can specify the convert argument, which will change the new columns to the most likely column type that R determines. Because these are numbers, it'll change them to integers. So again, let's look. Here we're gonna specify our F date. So same exact code as before. We're just adding a couple things to it. So F date, separate into month, day, year. Now we're gonna specify a separator. R automatically does it for whatever non-alphanumeric value is there. If you have a weird one or R is having trouble separating by it, just specify it here, SEP equals in quotation marks, whatever the separator is, which for us is a forward slash. And then we say comma convert equals true, and it's going to convert those new variables to integer rather than character. So it's going to convert them to something else. This can be really helpful when you are separating things like numbers apart, and it was a character or a factor, and you want to make them numbers, numeric, that kind of stuff. And then unite does the opposite. It allows you to combine multiple columns. So what we'll do is just combine month, day, and year again, just to show you what it does. So we're going to take our dates data set that we just made where they're separated. So again, month, day, and year are separate. And we're going to say unite. And what you do is you just list things. What you say first specify what you want your new column name to be. Date. Then you specify through listing, and there's no concatenate here. It's just listing the column names, specifically month, day, and year. And we want them to be separated by a forward slash. So what this does is create a new date column that is a character, and it put in month, day, and year. Here we could separate by anything. Dash. Now it's the dash there. You could have a space, so just put a space in there. We just have spaces in there. But this, you can combine whatever you want with unite here. So separate and unite separate pulls apart things within one column or one cell of data, and unite smushes multiple columns together. So this is it for the Data Management 2 module. So we talked about lubridate, separate and unite, as well as joining data sets, joining your related data. So we'll move on to more data management stuff in the next module as well.